Hello, everyone. Welcome to lecture 14 on finite element method. So in this lecture, we want to pick up where we left off in the previous lecture. But before that, we just have a quick overview of what we have done. So until we finish the one-dimensional finite element, I will always give you this overview. So I will always start with this slide with the map that we have basically and with the journey that we have. But the intermediate slides, every time that you see them, they are less of them. So basically I cut the intermediate steps, but I keep the most important ones. So we just go through what we have done very quickly now based on that. So again, the idea is to start from a differential equation or a strong form, and then basically from that strong form you derive the weak form, which is now an integral form, and you want to solve that. And then because we do finite element method, there are different sources of approximation too. To better understand what's going on, we started with a, let's say, simple strong form that's a second order ordinary differential equation. But this is also very important in mechanics. So it's basically describing the behavior of a simple mechanical structure. And then we explain that in order to derive the weak form, you have basically two steps. You need to multiply by test function and then integrate over the domain. And we showed that if you do those two steps, basically you get the weak form, which would look like this. Now, as an example, we looked into this specific example together. So we simplified that function. Instead of f, we have 1, and also we integrated over the domain 0 and 1 with specific Dirichlet and Neumann type boundary conditions. Also, it's a nice example because for this one, we know what the analytical solution is, and then you derive the weak form from that. And then for that weak form, we looked into different approximations. So one-piece linear approximation, then two-piece linear approximation, whether it's uniform or non-uniform or generic. And then we did the next one, so three-piece linear approximation, uniform, generic, and then four-piece and quadratic and cubic. So we did those, and then again, if you do the one-piece linear approximation, after a few steps, you get this. So you basically hit the solution at nodes. Then you do a two-piece linear approximation, then you get this. You do a two-piece non-uniform approximation, so it also looks good at nodes, at least you hit the solution. And then you can also do a generic one. Okay, it's another non-uniform, and then we also did a generic one after that for just any A. And also we see that that idea holds, that basically you hit the solution at nodes, but also it seems that in each piece, the area of the integral between your approximate solution and analytical solution, the area of the derivatives between these two, it seems in each piece is vanishing. So if you look at these triangles. So basically that constructs, or that constitutes the foundation of what we do with the finite element method. We also looked into three-piece linear approximation. A similar observation holds here about the areas, and also you can see that you hit the analytical solution at nodes. Obviously, by increasing the number of pieces, you get better approximations. The same thing holds if you have a four-piece. So that would be now a four-piece. And we also did it with a one-piece quadratic, and you can see if it's a one-piece quadratic, you just hit the solution itself, which tells you if the approximation space is large enough, then you hit the exact solution. We also showed the same story or the same conclusion with the cubic approximation. So even if you have a cubic approximation, it automatically reduces to the quadratic one, which again, it sort of confirms the message that we had previously. So this was all about how we did that. So we want to learn a better way, a new way, a different way of doing this. And this is what we want to do next. And the new way is also related to approximations, basically. So the way we did the approximations previously, we just called them two-piece linear and, I don't know, three-piece linear and so on. But let's say if we want to have many of these pieces, this was not very, let's say what we did before is correct, but it's not very, how to say, it's not very sustainable to just keep increasing this number. So maybe basically what we want to do is to find a better way to just have an n-piece approximation. And maybe those pieces, they are not equal in length. Maybe some of them are longer, some of them are shorter. Okay, so you can imagine that your mesh, your discretization is not uniform. That's what we want to do. In principle, what we want to do is similar to what we have done before, but basically we want to uh, sort of do a glorified approximation, if you want. So we want to do this approximation in a more systematic way. And in order to do that, we just discussed this a few simple examples. So let's say you have a function that is 0 at 0 and it's 1 at 1. Then if I ask you what is the value of that function at 0.5 or zero point 0.8, you can say 0.5, 0.8 without even calculating it. But basically what you have done is that you have, in your mind, you have set up the function u equals x by just seeing these 2 points. Then I do the same game, but now I change these numbers a little. So now you have to approximate those points, but then basically what you do in your head is to find the equation of this line. And if you have more points, now you want to fit a quadratic approximation to them. So it's slightly more complicated, obviously, but you know how to do that quadratic approximation. Let's say the way you have learned it before. You would say, well, I just construct my function. I put these three coordinates as three constraints to find the coefficients, and then basically you can find those coefficients and you get your function, then you are done with your approximation. But if it is cubic, obviously you can do the same thing, but it gets longer and longer and we don't want to do that. So let me just say, okay, if it is a cubic function, then now you would do something like f of x equals ax cubed plus bx squared plus cx plus d. Okay. So it's gonna work. So you would have to have like a four equations, four unknowns to calculate the coefficients. And if you have that, then you have f of x. And if you have f of x, then you can, of course, calculate that u that you wanted. So that's what we want to do today, but we want to learn a nice strategy to do it in a systematic way. And this is done through this concept of shape functions. So shape functions or hat functions or tent functions, this is basically a powerful tool for approximation, and it allows us to do it systematic, but also more importantly, it allows us to do this for 2D and 3D in a very similar way. So even in 1D, you see the power of this, you see the, let's say, the reason we do this or the logic behind this. But if you are not convinced for 1D, it's okay, because you actually see how powerful it is if you go to 2D and 3D. Whereas your previous approach, like something like this, if you want to go to 2D and 3D, it automatically or it immediately it blows up to a much larger degree, because you can imagine if you think of a 2D, now you want to construct the same quadratic or the same cubic function, you would have cubic terms in terms of x and y and then their multiplication and so on. So instead of four coefficients, you would have a lot more than that, and it's going to get almost impossible to approach those types of problems. Whereas if you use just shape functions, they work quite nicely. Okay, so after this little overview and let's say advertisement for shape functions, what is a shape function? So a shape function ni, it's a function which looks like hat. It has two properties. It's one at node I itself, or you can think, if you think of any point j, if j and I are equal, that is one. Or it's zero elsewhere. So at any point that is not equal to I, that is zero. So that is the way you define that. And here are the examples. So you can see, for instance, ni here is 1 at node I, and then 0 at any other j, which is not equal to I. So this is the linear version of it, but you can also think of a quadratic version of it. And once you have that, the nice thing is that if you want now a linear approximation, this is how you can construct a linear approximation. If you want a quadratic approximation, you can construct it like that. And if you want a cubic approximation, you can just easily extend the same approach. So let me make space and just show how a cubic one would work for you. So a cubic approximation now, in light of what we have here, would be u equals n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Okay. So that would be your cubic approximation.
Hocam, can I ask something?
Yes, please.
What J represents for J?
J is just a dummy counter, if you want. It doesn't do anything. It just tells you any point j. If j and I are equal, then ni would be 1. Otherwise, it would be 0.
It's not the
So
y-axis coordinate, right?
what's that?
It is not the y-axis coordinate.
No, it's a counter. So this is j. So each of them is a j. You see what I'm saying?
I see, thank you.
So again, think of I to be a number, maybe 5. So it tells you if j is equal 5, then that ni or n5 is 1, but n5 at any other point is 0. Does that make sense? So it says, so this basically tells you n5 at 0.5 is 1, n5 at any point that is not 5 is 0. It's basically telling you that. Does that make sense?
It makes.
Yeah. So basically, again, if you think of this I to be just number 5, you can see that this is a function which looks like this. So basically here at n6 is 0, at n7 is 0, at at 4 is 0, at 3 is 0. So at every other number that is not 5, it is 0. And only at 5 itself, it is just 1. So basically, this is the idea. All right. I mean, you don't have to think too much about the mathematical definition. The concept of it is much more important, that you just see it's a hat function which does that, because then because of that property, you would be able to do this. Because now you can say, well, I have a function which is 0 elsewhere and is just 1 at its own corresponding point. So it allows you to do this sort of approximation, because then this would look like weighting of that function on other nodes, basically, or other points in the domain. Okay, so as I mentioned, or as I promised, now you can see whether you want linear approximation, quadratic, or cubic, it's the same strategy. It's just a sum over I of NIUI. And for you, this sum is very nice because it basically means you have a loop. So you would go for I equals 1 until node per element, and then you do that summation end. So this is how you would program it, basically, which is quite nice for us. So let's think of an example here. A very simple example would be if you think of these 2 points at coordinate 0 and 1, node 1 and node 2. Now, if you construct each of these, they would look like 1 minus x and x for n1 and n2. And if using the coordinates, for example, 1 that we started with, if you use those coordinates, you can get the equation of your line, which is u equals x, and that is the equation you had, and it works out, obviously. And as I mentioned, now you want to play this game for higher order functions, but before doing that, we should learn how to construct these. So in order to construct this, you should just look at their property. What was the property that we talked about? N1 must be 1 at node 1 and must be 0 at node 2, let's say, or at a point with coordinate b. So in order to do that, you construct it like this. You would say N1 is x minus b. So this part makes sure that it is 0 at point with coordinate b, but then at coordinate a, the value of n1 would be a minus b. So in order to have it 1, then you also normalize it by that. So that's how you construct them, basically. You can construct n1 and n2 for a linear function like that, but then you can also do it and assuming that this was your linear approximation, so node 1 and node 2 are at coordinates b, a, and b. Then for a quadratic approximation, node 1, 2, 3 would be at coordinates a, b, c, let's say, in the next slides. And for a cubic approximation, nodes 1, 2, 3, 4 would be at coordinates a, b, c, d in the slides that I show you. So now this is just the way I plotted them. These functions are exactly what we just had. So this is n1 and n2 that we define together, and you can plot them. So if you plot them, you just see exactly what you see in these figures. And as you can see, the coordinates do not matter. So here you have a and b to be at 0 and 1. In the other one, you have a and b at minus 1 and 1. But shape-wise, if you look at them, it's the same shape, okay? Now, if you look at a quadratic function, a similar message holds, obviously. So again, whether the range is between 0, 1 or minus 1 to 1, it doesn't matter because you see again the same shape, but what you can also see is that they are 0 at, or each of these shape functions is 0 at other nodes. So for instance, if I think of, I don't know, n2 here, you see n2 is this one. So at node 2, it's here, right? Remember, we just had this order, basically. So at node 2, n2 is 1. And in the other two ends, it is just 0. Does that make sense? Very good. All right. So you can obviously change these coordinates of A, B, C, and I played with those coordinates a little. So you can see for each set of A, B, C, I have a different graph. But the important message for you is that in all those graphs, that key message holds. So here, for instance, if b is minus 0.8, that would be somewhere here. You can see that, again, the red function is 1 at that point, and at the other two, it is 0. So it holds that property the way we expected it. And you can also obviously do it with the cubic function. So if you do that with cubic functions, you see the same thing. Again, here, if the points are distributed in a similar manner, shape-wise, they have the same shape. As you can see, it doesn't matter if you do that between 0, 1, or if you do it between -1 and 1. You can also change those points and you get slightly different functions. So what I want to do next is to use this to now come back to that example that we started with and see if we can, using what we just learned, if we can construct these functions. So if we see, we want to see if this thing helped us to construct these functions. One of them we did already as an example, so I will go through that quickly. But let me just clean this up and then we do this again together now. So I can keep this. So let's do the first example, the one on the left. As we discussed, we expect u to be n1, u1 plus n2, u2. In this example, n1 is 1 minus x, and u1 is the value of u at node 1. Okay? Plus n2 is x, and u2 is the value of u at node 2. Now, the value of u at node 2, this is basically this. This is node 2. This is node 1. Remember, 1 is left, 2 is right, basically. It's 2 points. Now, basically, this means this is 0, this is 1, and your approximation would be x, and that is exactly as we expected. So here, ux is equal x. Done. Now, how about the next one? In the next one, now, again, we played exactly the same game. So u is, again, n1, u1 plus n2, u2. But now, in this case, n1 is that function which is, again, remember, this is u1, this is u0. So if you want to think about it, you want a function that is 1 at point 0, and you want it to be 0 at 1.6, and other way around. So this would be your n2, and this would be your n1. Okay, so I don't know, you get the idea. So now n1 in this case, if you want to construct it, remember how we did that? So we would say it is x minus 1.6 because we want to make sure it is 0 at 1.6, so it ensures that. But then at 0, if you just insert x equals 0 here, you get minus 1.6. Whereas we want it to be 1. So we need to also divide it by 1.6 or minus 1.6, basically. u1, and u1 is just the value of u at point 0, which is 1 in this case, plus, now you construct n and 2, you do exactly the same thing. You want it to be 0 at 0, so x minus 0. And then at 1.6, you want it to be 1, so you divide it by 1.6 times u2. Now here u1 is the value of u at node 1, that's 1. u2 is the value of u at node 2, which is 5, And if you just do the math, you would get 4 divided by 1.6 x plus 1. So here your function would be ux equals 2.5 x plus 1, which justifies these numbers. So, sorry, it would be 2.5 x plus 1, which now tells you why this happens. So let's say at 1, 2.5 times 1 is 2.5 plus 1, that's 3.5. At 0.8, which is in between the two, and let's say intuitively you said 3 before, now you can also see that. So 2.5 times 8, it would be 2 plus 1, that gives you a 3. Okay, so this is a nice way of constructing these functions, and now we want to do the same thing for the last one, for the quadratic one. Let me make space for that. Let's just shift these a little to have space there. Okay, so the last one, the cubic one. For the cubic one, we play the same game, except that now we have one more function. So it would be n1, u1 plus n2, u2 plus n3, u3. Okay, so this step is not too complicated. And then again, the nodes are, this is basically node 1, so that is u1, this is u2, this is u3. And if we want to write those functions, now again, remember how we write those functions. N1 is something that is 0 at these 2 points and is 1 here. So how can we write that? It would be x minus 0.5 times, so let me just make this smaller, and we write everything a little smaller here. So n1 is x minus 0.5, because it must be 0 at 0.5 here, times x minus 1, because it also must be 0 at 1. But then it must be 1 at 0. So what you need to do is to insert 0 here. If I insert 0 here, I get minus 0.5. If I insert 0 here, I get minus 1. So you multiply them, you get 0.5. That means you need to divide this by 0.5 to have your shape function. So that is n1. N2, again, a similar game. It must be 0 at 0, so x minus 0 then in the denominator. Sorry, my pen changed that. 0.5. And 2 is 0 at point 0, it's 0 at point 1, so you divide by also x minus 1, and now you insert 0.5 in it. So if you insert 0.5 in this and this, you get 0.5 here, you get minus 0.5 here. So that gives you minus 1 over 4. That means you need to divide this by minus 4. Sorry, minus, that gives you minus 1 over 0.25, which is like a 4 in the denominator. So okay, here is you have 0.25, which is 0.5 times 0.5. All right. So that's that. And then you have N3. Now N3 must be 0 at 0. It must be 0 at 0.5. Then it must be 1 at point 1. So if you insert 1, in the first one, you get 1 minus 0, that's just a 1. Here you get 1 minus 0.5, so that's 0.5. So you divide it by 0.5. That is your N3. Okay. Now that you have all those three N's, all you need to do is to just insert them into this form that we have down here. So if you do that, again, remember U1 is just 1, U2 is 2, U3 is 4. So all you need to do is to insert those values, but also remember they have these numbers. So for instance, here when you insert 1, 1 divided by 0.5, that gives you a 2. When you insert this one, 2 divided by minus 0.25, that gives you something like 8 or minus 8, basically. So I'm saying that because I'm going to write them now, let's say by inserting them, but I want you to know where those coefficients are coming from. So 2 is just 1 divided by 0.5. It's not anything complicated. So this would be the contribution of the first one. Then for the second one, you get minus 8, x squared minus x. And then for the third one, you get plus 8, x squared minus 0.5x. Okay, so this step is just inserting values. It's nothing that complicated. It's even more importantly, it's nothing that you must do. Here, I did it to just show it to you, but it's nothing that you must do, really. And if you do the the simplification, then obviously you can just see ux is now a quadratic function, which looks like 2x squared plus x plus 1. Now, if you remember, we also solved this example together previously using our old approach, so having just 3 equations, 3 unknowns. And we ended up with the same function. So that's what I'm trying to say here, that what we do here is just a different way of approximating that function. But what we do now, or what we did now using shape functions, it's far more systematic compared to what we did before. And the reason for that is this, as I mentioned before. Previously, when you did these 3 equations, 3 unknowns, you had to solve it. You cannot just say, well, this is my approximation. So there is still a huge difference to talk about this function and then solving it based on the 3 constraints and then say, this is my result. Previously, it was like that. What you have now is different in nature because once you write this, you do not have to do these steps. It's not that you are solving anything. We are just simplifying it. So in other words, from a computer perspective, so if you are programming this form or this form or this form, they are identical. So it's not that we solved anything new to come to any of this. So for your computer, this is the approximation. So this is exactly the result. Okay, and you can see, in order to get this, we did not solve 3 equations, 3 unknowns. We just used exactly what we had in our problem. We used the coordinates, we used the shape functions. So you define these shape functions once in your code or in your lifetime, basically in your programming. It's at the beginning of your code, and you can always read them for the next of the derivations. But also, even more importantly, what I'm trying to say next is that you can play this game for that cubic function, which otherwise it would have been almost impossible to play. So if now we look into the next example, which was the cubic function. So imagine you have that now, this cubic function, and I ask you, what is the value of u at 0.8? As I mentioned, the standard way is to just start with this. Then you do 4 equations, 4 unknowns, which is usually very complicated, and you need to solve that. But what we are going to do now is a much more systematic way of doing it. So in order to do this, we do the following. So you know these 4 points. Now you would basically say, well, these 4 points are your points or nodes 1, 2, 3, 4. So this is node 1, node 2, node 3, and node 4. And for each of them, all you have to do is to define that, the shape function. So here you want to say what is n1. Then you find what is n2, what is n3, and what is n4, which we just learned how to do it. And once you do that, you just write the result like this, that u is equal n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. And you are done. That's all you have to do. Okay, so this is perfectly fine. Now, obviously, like I did in the previous example, if you want, you can also simplify that, like we did here. You can do these 2 additional steps, and if you do those additional steps, you can, of course, also write it as a function which would look like alpha x cubed plus, I don't know, beta x squared plus maybe gamma x plus, I don't know, maybe c. Of course, you can do that, but this is just our, let's say, additional redundant or human step. Okay, so this could be an additional step which is completely unnecessary, if you want. So when I say unnecessary, I mean unnecessary from a computer perspective. Does it make sense? So what I'm trying to say is that for you, This form seems like a more familiar form, more friendly form compared to this. Whereas for your computer, they are the same. In fact, maybe this is more complicated for your computer than this one, because for this one, he can go, or your computer can go over a loop and can calculate that. So in other words, once you are here, you are done. You do not have to do this additional step, which solves or which saves a lot of time for you. So the only step to get there is to define these shape functions, and that's what we want to do just quickly together. So how to do these shape functions for this coordinate? Again, remember you want to calculate n1. It must be 0 at 0.2, 0.6, and 1. So what is the easiest way of writing that? You would just say it is x minus 0.2, x minus 0.6, x minus 1. Okay? Now, you know it is going to be 0 here, 0 here, and 0 here. That's what we wanted for n1. But also we want it to be 1 at node 1, which is 0 coordinate. So you insert 0 in this. If you insert 0, you get minus 0.2, minus 0.6, minus 1. So altogether, this gives you minus 0.12, which basically tells you you need to divide this by minus 0.12 to normalize it such that it gives you 1 at node 1 with coordinate 0. That's all. Then we do the same game with the second one. So n2 is now a function which is supposed to be 0 at coordinate 0, coordinate 0.6, coordinate 1. Okay, so it must take this form. X minus 0, x minus 0.6, x minus 1. And then you play the same game. You insert 0.2 in this, you calculate it, and you divide it by that value to make sure that it is giving you 1 at node 2. And that value is 0.064. Then you do n3. Again, it must be 0 at here, here, and here. So you would have x minus 0, x minus 0.2, x minus 1. So x minus 0, x minus 0.2, x minus 1. And then you evaluate that at 0.6 and divide it by that number to make sure it gives you 1. And then finally, we do it for n4. Let me just make a little more space here. Okay. So if you do it for n4, then again, n4 is 0 at 0, 0.2, and 0.6. So that would be x minus 0, x minus 0.2, x minus 0.6 divided by now 0.32. Okay. So this is basically all you have to do to have this third order polynomial. And as I mentioned before, this relationship is in principle is exactly the same function you have here. So it's a cubic function with 4 specific coefficients which can come out of your calculation. It's just a different way of constructing it, but it's the same thing, or it's a more systematic way of constructing it, but it's exactly the same thing. All right, so what we want to do next, now that we have learned a nicer way, a more systematic way of writing approximations, we want to go back to our example here. We want to go back and solve that again using this way of approximation, using our, let's say, our new approach to approximation. Remember, we had this example and we did, for instance, one-piece linear approximation and two-piece and so on. So we want to do two of, or three of them actually, one-piece linear, two-piece uniform linear, and also we do one-piece quadratic. So we just do three examples now, but we do it in our new way. And you can then compare the new approach, which is much more systematic based on shape functions. You can compare it to what we did before based on, let's say, elementary calculus or high school calculus. So this the way we do it now. The new way is more interesting in that sense. And we will do that after the break. So it's 9:20 now exactly. Let's have a 10-minute break. We will continue at 9:30 sharp. All right, so we are back. As I mentioned before the break, what we want to do next is to solve this example using our new approach. Before doing that, let me remind you of what we did previously. Maybe a little rectangle here. Okay, so what we did previously, remember how we did before. So previously, we start with something like the W, and I'm talking about a linear approximation, for instance. So let's just think about a one-piece linear approximation for now. If it was a one-piece linear approximation, we did like W equals C1x plus C2, and then we said U equals D1x plus D2. And then you inserted this into your weak form. Which you had from 0 to 1. Again, if it was one piece, you would have just one of them. And then we use the fact that this holds for every W. So the fact that the W was arbitrary. And from that, we basically ended up with, after some steps, or after solving the equations, we ended up with the coefficients D1 and D2. Okay. I mean, in this particular case, maybe you remember D2 was actually 0 because of the condition that we had on U itself. But then, okay, we calculated D1. But it's important for me that you remember what we did before. Okay, so what we did before was to construct these linear functions in our usual way of constructing a linear function, and then you calculated the coefficients, or you dealt with the coefficients themselves. What we will do now, or what we will do next, based on what we have learned, is different in a sense that we will use the coordinates, or the values of the functions at points, not the coefficients, as the unknowns of the problem that we want to deal with. And you can imagine that has a huge impact, or let's say advantage for us, because the unknowns are nodal coordinates in the next approach that we want to do. Okay, so let me do that, and then because this one-piece linear is pretty straightforward, maybe I try to fit it within this same slide. So let me just do it here. So we don't want to do it the purple way that is on the left hand side. What we want to do is to do the following. So you have this domain from 0 to 1. And then again, 0 is your left node, 1 is your right node. And let's number them like this, that the right node is the node 2, left node is node 1. Now you construct those shape functions that we had. Remember, this would be your n1, and then this would be n2 basically. So this is n1, this is n2. And pay attention, I am putting the node number as a superscript. Okay, so this superscript is always the node number basically. So it's kind of in accordance with what we have done before. Okay, so if you write these shape functions, you can immediately see that n1 is 1 minus x. I mean, this is basically what we just had before, and n2 is x. Okay, so it's not difficult to just write these two functions. But now, for w and u, instead of writing them like this, I want to write them in the new way that we just learned together. So what did we say? We said, well, you can say w is n1 w1 plus n2 w2. And u can be n1 u1 plus n2 u2. Now, in this approach, w1 is w, or the value of w at node 1. So this means w at node 1. This means w at node 2. And then you can imagine this means u at node 1, and this means u at node 2. Okay, this is exactly the way that we just learned together how to write these functions. Remember what we did here? This is exactly that thing. Okay. So that's that. Now, at node 1 here, node 1 is this node, the node at 0, which has a prescribed displacement. So it's a Dirichlet type boundary condition. So you know w at node 1 is 0. So this would be 0. Because, as always, w at Dirichlet type boundary condition is 0. Let me change to my earphones. There is some construction in the background. Maybe you can hear them. All right. So for U1, now we play the same game. For U1, you know already what the value is. So here U1 is just 0. It's the displacement at point 1. It's given because we know U0 is 0. Okay, so basically what you have is a shorter version. You can just say then W is into W, and that means for you, W is just X W2, and U is, well, in a similar manner, is now just N2 U2, which is simply X times U2. All right, so what you want to do next is to insert these into this integral as we did before. So let's do that. If you do that, then you get integral from 0 to 1. So if W is xw2, what is W prime? W prime is just W2, right? It's just there. Remember, W2 is a coefficient, is a number. It is the value of W at point 2. So the derivative of this with respect to X, it would just give you W2 itself. So here you get W2 for the U the same. So U prime would be simply U2. Then you integrate that. That's equal integral from 0 to 1. Now you insert W here, obviously, which is xw2 dx. Okay, so this is your weak form. Now, if you integrate this, these are constants, so these are coefficients, they come out of the integral. So this thing gives you integral of x from 0 to 1, which is just 1, basically. So that would give you W2 U2 equals the one on the left-hand side. Well, again, W2 comes out. Now, integral of x dx, that would be 1/2 x squared. From 0 to 1, that gives you 1/2. Yes, that gives you 1/2. So this is basically 1/2. Let me just write it. So it gives you something like W2 1/2 x squared from 0 to 1. So that would be then just 1/2. Okay. So I'm going to just write then 1/2 here. So what can you see next is that, remember, this thing must hold for any W2, by the way. This step that this must hold for any W2, it may seem redundant, but basically it tells you that W2 may or may not be 0. So if it is not 0, let's say, you can cancel it out, and then it tells you U2 must be 1/2. All right, so that's it. So now that you know U2 is 1/2, let's come back one step to this. Remember, the relationship for U was X times U2. So basically what you need to do next is, if you want to do, you don't have to do it, by the way, but if you want to do the next step, is to just insert this value into your U function. Okay, so if you do that, And let me just make a little space here for doing this. Then you can see that u would be 1/2 of x. Again, this is an additional step or an optional step for you if you want to do it. You should pay attention that from the viewpoint of the finite elements method, this is your answer. So the unknowns are the value or the values of displacement at nodes. So here your unknown displacement at node 2 is 1/2. So the problem is solved. Again, maybe you would be interested to see this line, but this is our, let's say, our human nature. For a computer, it doesn't matter. So this line is less useful for a computer than this point, basically. And then again, remember the unknowns of the finite element method are nodal values and nodal displacements in the first place. And if you just plot what we had, you basically come to the same thing. Remember, we had this plot some lectures ago when we basically solved this problem, but we solved this problem using our previous approach. And this is kind of the message I want to convey here. If you do this using the previous approach, of course you get the same function. You can plot it and you can get all the, let's say, all the insights, and you can come to all the conclusions we had before. But I hope you can see the difference, or let's say the fundamental difference between these two approaches. So in the previous approach, the unknowns were D1 and D2. The unknowns were coefficients. Here in this approach, the unknowns are nodal displacements, are basically U1 and U2. There is a shift of, or let's say there is a paradigm shift of how you look at the problem. And you can imagine if you want to solve a problem, a structural problem, this is a much more meaningful description of a problem for us from a computational perspective, because again, if you set up the problem as the way that we did, so that the unknowns are the nodal displacements, then solving the system would give you those nodal displacements immediately. You don't have to have those, let's say, intermediate steps. So what I want to do next is now basically play that similar game that we did before, but I want to do it with a two-piece linear approximation or two-piece linear uniform approximation. Remember, I said we want to do these three things. So we did the first one. Now the next thing I want to do is this two-piece linear uniform approximation using the method that we have now. So this is two-piece linear uniform approximation. And then again, what we want to do, or let's say that first step to approach this problem is to properly write the shape functions. So again, let's say this is the domain, and maybe this is 0. Let's say this is the last point. Okay, this is the point in the middle. So this would be node 1, node 2, node 3. Coordinate wise, let's say this is at coordinate 0, this is at coordinate 0.5, and this is at coordinate 1. Now, the three hat functions or shape functions, they would look like this. You would have a function which would be 1 at node 2 and 0 at the other two nodes. So that would be your N2. Okay, so this is our N2. And I use different colors to identify that they are different functions. Then N3 would be 1 at node 3 and 0 at other nodes. So it would look like this in this domain. So that would be N3. And then let's use, I don't know, maybe purple for, or gray for N1. So N1 would be something like this. So this is your N1. Now all you want to do is to write their functions, obviously. And then once you have their functions, the next step would be to do the approximation the way we did. So N1, if I want to write N1, you need a function. So I'm trying to think how I can make this. Let me write N2 because it takes more space. So N2 has two pieces. It has this left piece, which is 2x. And then it has this right piece, which is minus 2x plus 2. Okay, so minus 2x plus 2, again, as you can see, if x is 0.5, then you get minus 1 plus 2. It gives you 1, so it gives you 1 at node 0.5. And then if you look at this one again, it also gives you 1 at node 0.5. Okay, so that is N2. N3, if I can just write it here, that would be 2x minus 1. Again, you can see that if x is 1, that gives you 1. And if x is 0.5, that gives you 0. Now, for N1, you can imagine that N1 must have the same slope like N2. So it would be something like minus 2x plus something. But then at 0, you want it to be 1. So it would be minus 2x plus 1 maybe. So let me just see if that works. So N1 would be minus 2x plus 1, I think. And if you have that, you can see that at 0.5, it is 0. So that's what we want. And at 0, it's 1. So that's also what we want. Okay, so this is basically how you should look at it. Now, the important thing or the different thing here is that you have a two-piece linear approximation for N2 because we are talking about a two-piece linear approximation. But that shouldn't really confuse you because you should look at this approximation like this. It's like you do the first integral and you do the second integral. So this would be integral from 0.5 to 1. This would be integral from 0 to 0.5. Remember, it's a two-piece linear approximation. So you do that split of domain. And anyway, in each domain, it looks like this letter X, right? So you always see this X-like structure, which you saw also here in each piece. So it's not complicated, really. Okay, so now what we want to do is to just solve this or approach this using what we learned. Again, W would be now n1 w1 plus n2 w2 plus n3 w3, and u would be n1 u1 plus n2 u2 plus n3 u3. Similar to before, because of the boundary conditions, you know that u1 is 0. So we know displacement at node 1 is 0. Here, this is given. Let me see if I can make this also, or I can put this on the corner. Of the next slide too. Okay, I'm going to put this on this corner to just remember what we do. So that's that. And then because it's a Dirichlet type boundary condition, also then W1 is also 0 at 0. So that simplifies these two lines. So basically you would have a W that is just N2 W2 and then N3 W3. And then you have a U which has now two unknowns basically. And then again, pay attention that now the two unknowns are not two coefficients of just some sort of line slopes. These two unknowns, they are exactly the nodal displacements. So upon solving the system of equations, we get nodal displacements immediately. Okay, so you want to write this integral or the weak form. Remember, the weak form is integral from 0 to 1 w prime u prime dx equals integral of 0 to 1 of w dx. But for us, we have to split it into two domains. So you would go from, let's say, 0 to 1/2 on the left-hand side and on the right-hand side. Because it's a two-piece linear approximation. And then if you do that, okay, you get something like this. Integral from 0 to 2, 1, w prime u prime sorry, from 0 to 1/2 w prime u prime dx plus integral from 1/2 to 1 w prime u prime dx equals integral from 0 to 1/2 w dx plus integral from 1/2 to 1 of w dx. Okay, so what are these w prime u prime in each? So between 0 and 1/2, or let me just do it in a more generic way. You can always think about it this way, that w prime, remember w is n2 w2 plus n3 w3. So w prime is just the derivative of that, which would be n2 prime w2 plus n3 prime w3. Okay, the same holds for u. So u prime is n2 prime u2 plus n3 prime u3. Now remember, if for instance here if you have n2 to be 2x, n2 prime, it would be 2. n2 prime here, it would be minus 2. Okay. So you can simply write these functions like that. Okay. And then you write each of them using this format for each of the integrals. That's what we want to do next. So let me just make space here a little. What I want to do is to basically combine these two steps. I want to write this integral in terms of such derivatives, and then we want to go through the calculations and solve this together. So let's do that. So you would have this integral from 0 to 1/2. That would be n2 prime w sorry, n2 prime w2 plus n3 prime w3 times n2 prime u2 plus n3 prime u3 dx. That would be basically this integral. Okay, and then I will write the other terms too now, just so that you know that's the way we are going to construct this. So that's the first one. Then you would have plus integral again from 1/2 to 1. Now pay attention that the second time that I have to write this, it's exactly the same thing that I wrote before. It's just over a different domain. So all I have to do is to just copy paste that thing. Now this was the left-hand side. The right-hand side is integral of w dx. Now w is just n2 w2 plus n3 w3 itself times dx. This is between 0 and 1/2, and the other one is from 1/2 to 1 of the same thing. All right. So obviously the derivations are a little long, but the message is important, and also obviously we don't keep writing it every time. It's the first time that you see it, and I want you to understand the intermediate steps. Okay, so let's insert the values of these functions. So what is n2 prime from 0 to 1/2? And then what is n3 prime from 0 to 1/2? Remember, n3 is this. So basically it is 0 everywhere else. So n3 prime from 0 to 1/2 is simply 0. Okay, so this is 0. This one is 2. n2 prime is 2. n3 prime here is 0. Then n2 prime, well, the same thing now here, but for the second half, n2 prime is now minus 2. n3 prime is 2. n2 prime is again minus 2 and 2. Okay, and n2 and n3, you already have them. So n2 between 0 and 1/2, this is 2x, whereas n2 here in the second integral is minus 2x plus 2. n3 in the second integral is 2x minus 1. In the first integral is 0. Okay. So you have these. Now, if I sort of go through the derivations and simplify them a little, it's actually pretty quick to see how they simplify, because you have these zeros. So you have terms that vanish together, and here you don't have that, but you have that nice symmetric structure. So if you do it, or let me just do it and write the result. The first two integral, they will look like this. So the first one would be 2w2 times 2u2 dx. The second one would be take everything down a little. Would be slightly longer, but not too bad. So minus 2w2 plus 2w3. And a similar thing, but now with the u instead of w. Okay. So that's that. This is essentially the left hand side. The right hand side, now you need to do the derivations. Here it is 0, so it goes away. Here you have integral of 2x, that gives you x squared basically. And here you do the same thing, so minus 2x, that's minus x squared, then it gives you plus 2x, and so on. So on the right hand side, you just have that integrals. So if I want to write it, then again it's also, let's say, integral from 0 to 1/2 2x w2 dx plus integral from 1/2 to 1 . And from 1/2 to 1, you can see you have two integrals. So one is minus 2x plus 2 times w2 dx, and then the other one would be corresponding to w3, which I'm going to just write underneath. So plus integral again from 1 over 2 to 1, 2x minus 1, but now it would be multiplied by w3 dx. Okay, so this is what you have. All you need to do now at this step is to solve it. And the next step is pretty straightforward. So solving it is just to do these integrations, and they are super simple, as you can see. So here you have 2w to 2u2, everything is constant, everything goes out. So the first integral gives you something like, well, from this one you get 4u2 w2, and then integral of the x from 0 to 1/2 is just 1/2. Okay, so from the first thing you get something like 2w2u2, and then you do the same thing. So here again everything is constant, so basically they come out, they sort of simplify, and here you have integrals which have just x, so also not very complicated. So if you do this integration, and I skip through that step, but then again it's pretty straightforward. If you do the integration, and by the way, later we are going to learn how to do these integrations numerically, so you don't have to worry about it really. But imagine that we just do that, then you end up with something like this: 2w2u2. This is the first term that I just explained to you how you get it. Then you get 2w2u2 minus 2w2u3. I hope I'm not making a mistake here. 2W3U2 plus 2W3U3 equals 1/2 W2 plus 1/4 W3. But remember, W is arbitrary, so we need to impose that, and that condition that this thing holds for every W2 and W3, that's an important condition for us that allows you to basically solve this. Again, this looks like just one equation, but it is more than one equation because of that property, because we know that W2 and W3 are arbitrary. And in order to make it more, let's say, more telling, I'm going to adjust these terms a little. So this equation that we have, you can write it like this too. You can say it's all W2 times 4U2 minus 2U3 minus 1/2 plus W3 2U3 minus 2U2 minus 1/4, and that would be equal 0. And then again, this holds for every W2 and W3. So if you look at this one now, again, it looks like one equation, but now it is very clear that you can write it as just two equations, two unknowns, because now if this thing is supposed to be 0 for any W2 and W3, this means each of these coefficients must be 0, and that is exactly what I'm going to do next. So basically this gives you a two equation, two unknown system. And then again, at this point, my hope is that I'm not making a numerical mistake or a writing mistake here, but you get the idea, even if I do. Okay, so you have now these two equations, two unknowns, and from that you can calculate U2 and U3. So U2 would be 3/8, and U3 would be 1/2. Okay, and then again, this is very important for me that you realize what this means for you. What this means for you is that from this, you already have your U as a function of X. Because you see, this is how your U is constructed, and this is how the shape functions are. So the unknowns are the nodal values. All right? And then that is what you want to calculate. So let me just summarize this, and then we do the cubic one in the next lecture. So let's look at what we wanted to do. We wanted to solve this problem using our new approach for one-piece linear, two-piece linear, and one-piece quadratic. So we did one-piece linear, we just did two-piece linear now. We remain with one-piece quadratic, so I'm going to, let's say, prepare it for the next lecture. So this would be what we want to do next. We want to go through this with a one-piece quadratic function. Okay, and now for that one-piece quadratic approximation, Also, the approach is very similar to what we did before. The first step would be to define the shape functions like we did here. And then once you have the shape functions, we proceed from there. But before I do that, and then again, this is, as I mentioned, this is what we will do, what we want to start in the next lecture. But I mentioned this many times, and I want to just summarize that again, because it's important to connect what we have done previously and what we are doing now using our systematic approximation. So in the previous approach, and by previous, I mean a few lectures ago, and when we did all those nice exercises together, we had something that looked like this. So we had u equals, I don't know, alpha 1x plus beta 1, and we had, I don't know, another u, maybe alpha 2x plus beta 2, and this was between, let's say, x between 0 and 1/2, and the other one was x between 1/2 and 1. And then after doing all the magics and all the steps, we calculated the coefficients. So alpha 1, alpha 2, beta 1, beta 2. Okay, I mean, from that, of course, you could also calculate nodal values. And then compute nodal values. Remember? And then those nodal values, they just happen to coincide with the analytical solution, and then we said we have a super convergence and something like that. But this is important for me, that you realize this is what happened previously. So the nodal values were computed as a result, as a post-processing, if you want. So what do we do now? So in the current approach, what we have is something which looks like u equals n1, let's say u1 plus n2 u2. Okay, and okay, you have it for each piece. Let's say you have it for piece 1 still, like we did before. But for each piece, you can write it in a similar way, which is quite nice too. So in terms of just writing it, it's the same thing. The only difference is that, for instance, those functions, they could just change their, you know, their nature between these different pieces. And let's say if you want to talk about this 2 piece, you can actually write it like that. Okay, so let me let me add it with the third one to make it more clear that it's n1 u1 plus n2 u2 plus maybe n3 u3. But then again, remember, in the first piece, you n3 is 0. So in the first piece, only this part counts. In the second piece, only this part counts. So it's always a two-term sum for each piece. Okay, and now when you do this, after calculations, what you get is simply the values. So you obtain, so here you calculate U1, U2, and U3. Okay, so it turns out that here you calculate the nodal values directly. If you want, then you can still then compute U if you want to. You can still compute U as a function of X. You can still say, well, U of X equals, or you can find some functions for U in the first piece. Because you have already the shape functions, it's very easy to write those. And U equals Ux in the second piece. Okay, but what I want to emphasize here again, for the last time, I guess, is that this is completely arbitrary. It's unnecessary to do that. Okay, this one is a unnecessary step. This is just, you may want to do it just because you can, or maybe you want to plot it the way we do in a 1D. But this one, on the other hand, this is not a choice. This is exactly the unknowns of the problem. So if you have a problem, I give you a structure, I ask you to calculate the deformation of the structure or displacements of the nodes. So you have to compute the nodal values. Now, if you do it in the first approach, then it comes at the end. But also remember that first approach was very complicated, or systematically, it was not as straightforward as the second approach, because now in this approach, you can always write something like this. It's very systematic, and we can learn that it's almost impossible to program the first approach, whereas for the second approach, you can readily write it as a program, and then the integrals that you have, because now in their nature, they are different from what you had before. So these type of integrals, you can integrate these numerically. These are, so yeah, these integrals, they can be calculated numerically. So this is quite helpful for us. Okay. So this is the step that I'm talking about. Later, we can do numerical integration here, which again, it fits, or it just wraps up everything together, and you see the logic behind everything that we do, because that is, I think, the most important aspect of our formulation. We want to make it programmable. We want to make it systematic so that we can just code it together in MATLAB, as we will do. That's all for our lecture today. As I mentioned, in our next lecture, we will start here. We do this one-piece quadratic approximation, and then we go to, let's say, numerical approximations and integrations and so on. Thank you very much for your attention.